Hi. Okay, so I'm going to share with you how to simulate the three-phase half control or three-pulse rectifier, and the load that we're going to use is a purely resistive load. So this is the circuit and the thyristors. So we name it as a thyristor R, Y, and B according to with respect to the three-phase supply, and then we have the input, the purely resistive load, and this is the pass to each of the thyristors. So we have alpha, the firing angle for red thyristors, and then we have alpha plus 120 degree and alpha plus 240 degree. So before we go further into the simulation, we need to understand how this alpha or the pulse is supplied to the thyristor RYB. Why we need that 120 degree and plus 240 degrees. So let's refer to the waveform, three-phase waveform. So yes, we can draw the three-phase supply voltage waveform by drawing the triangle, isn't it? We draw the triangle, and then we can and then we connect the tips of the triangles, right? And then we just smoothen the triangles to make it as a sine wave. So that's how we draw the three-phase supply voltage waveform. And this is the region of thyristor. I name it thyristor 1. We label it as a thyristor 1, thyristor 3, thyristor 5. And this is actually to follow the labeling of the 6-pulse rectifier, the full wave rectifier or the full bridge rectifier. It is always labeling as a T1, T3, T5, and we have T2, T4, T6. Because by doing that, then we can see on the waveform the regions of the operation of the thyristor. Each of the thyristors will be labeled as this. So we need how we can identify the region of operation is by looking at which, for the top group here, which thyristor that have the highest or the most voltage, positive voltage, that phase will be turned on, isn't it? So from 30 degree to 150 degree, that will be the firing angle or the operation of thyristor 1, and from 150 degree to 270 degree, because yellow is at the highest, so thyristor 3 will only operate with this region, and then follows by T5. So blue waveform at its highest, so T5 only can be turned on from 270 degree to 390 degree. And at the bottom group, we look at the lowest positive that will be turned on. So in this case, at the beginning, so we have yellow phases operate at its highest, lowest. So T6 will be connect to phase B, isn't it? Yeah, the yellow phase, T6, and then it follows the T2, which is the blue waveform. Blue voltage is a minimum or the lowest, and then we have the lowest voltage at T4, the lowest voltage at T6. So that is why we label as such T1, T3, T5, T2, T4, T5, T6, and when it reflects to the waveform, when we draw, then we can see a nice sequence of T1, T2, T2, T3, T3, T4, then we have T4, T5, T5, T6. Right? So if you mess up with the labeling, you won't get this the label or the marking of the thyristors will be arranged in this manner. So you'll be mess up T1, T5, T2, T3, and the rest. So we label this as T1, T3, T5, T2, T4, T6, and if we rearrange that, actually the top group, and this is top group, so the top group actually reflect or very much similar to the three pulse half-wave rectifier. So that's why we also label for the simulation later on. We're going to label it as a T1, T3, T5, yeah, for the 3-pulse rectifier. Okay, so now let's try to understand the pulse to the switch. So we know that this in simulation, the gating block here, this is known as a gating block. They always refer to the reference point of reference of 0 degree is always at 0 degree of the red phase voltage, right? And therefore we need to delay by 30 degree so that it will start thyristor 1 will start at that point. So this is the point when alpha equals to 0, isn't it? So this is alpha equal to 0. So in the gating block in the Psim, we can put in this way. So we have 30. This is because the gating block always refer to that 0 crossing of the red phase. Therefore, we have 30 degree plus 10 degree. So that actually tells us the alpha is actually 10 degree. And for the tester 3, it starts at 150 degrees, right? So that's why we have 150 degree plus alpha. And lastly, we have 270 plus alpha. 270 plus alpha. In this case, alpha is 10 degree. And what is this 32? This is to tell us that it is only the width of the pulse is only 2 degree because we are producing a short pulse. This is known as a short pulse. We can also have a continuous pulse, which is a long with pulse. Short pulse, a long pulse, or continuous pulse, right? For thyristor 1, we can try this, and when we do the later on analysis, we might want to use the 120 degree pulse width. Okay, 120 degrees, no problem. So we just start with a short pulse, 30, 32, and therefore 150, 152, 270, 272. And then we connect to the 10 ohms. No problem with the 10 ohms. You can put any numbers there, but it reflects the output power actually. But in this case, we don't care about the output power, so we just put 10 ampere. So, and this is the waveform for the line-to-line voltage. So if you follow exactly the degree, the angle, and this is the pulse for the output voltage of a 6-pulse full wave rectifier. So here we in one cycle from here to there, we have 3 pulse, 1, 2, 3 pulse. That's why it's known as 3-pulse rectifier. And for the 6-pulse rectifier or full wave rectifier, in one cycle, which is from 0 to 360 degree, we have 1, 2, 3, 4, 5, and this is half, so 6. That's why it's known as a 6-pulse full wave rectifier. Okay, so once you understand and you're aware of all the degree, all the angles, then it will help you to how to do the simulation, how to connect the gating block, how to what we call it, program or put a parameter for each gating block there, so that you can trigger alpha 1, alpha T1, T3, T5 correctly. Okay, so there are 2 circuits, simulation circuits that I'm going to share with you. The first one is known as a that use the discrete thyristors. Okay, once you understand it's the discrete how to control each of the thyristor, what sort of control pulse that you need to supply for each thyristor, then it will be easier for you to understand for 6 pulse, and you will more understand on the waveforms and how these thyristors work. And this is the other version whereby you only supply alpha, the firing angle for the thyristor 1 only. And to do that, we only use the block set. So instead of 3 discrete single device individual thyristors, we use the block set. So in this block set, we have 3 thyristors. You can choose insulation. In Psim, you can choose a half bridge or half wave block set, or full wave full bridge what we call it, block set, right? And so here you only supply alpha value, and we have a control circuit here. This is where you measure red and blue, because we need to know where is the location of 30 degrees. So we sense R and B, and then we do the comparison here. There's a sensors V red, V blue, and that will be compared to 0. And then this is comparator, so that comparator will trigger the alpha controller here. And this voltage determine the degree, the angle of the alpha. So the voltage here determine what sort of degree that we're going to produce for the and supply to the thyristors. Okay, so we start with a discrete circuit, and then we go to and then we proceed with the block set. Right, so let's go to the Psim. So this is a Psim, the demo version of Psim is version 11. I think now you have a 12, version 12. No? So we start with new circuits, all right? You can click that, then there will be a new worksheet will be appear here. First, you need to add the sine wave. Okay, you can have a single source, so you need, but then you need to configure each which red, yellow, and blue. So yellow will be 120 degree phase shift delay, isn't it? And further 240-degree delay for the blue phase blue phase voltage, right? So if you want to have an individual source, and you can also choose, go to elements, and then you go to sources, voltage, and you can choose 3-phase sine wave, right? Click that, and you have 3-phase sine wave. In this case, double click, then you can tell the Psim the line to line voltage is 415. We have a frequency of 50 Hertz, so change that to 50 Hertz, display it, right? Click here, so you want to display that, and change that to VS. Okay, V supply, then close it. So yeah, 50 Hertz, 415. Next is to have the thyristors. So before we proceed again, let's forget about the voltage probe, current probe. We connect the main circuit first. The main circuit, we connect the main circuit so that then you connect the voltage probe and current probe, right? So we want the thyristor. So thyristors, you go to elements, power, and then power, then you go to switches. There will be a thyristor here, right? Click thyristor. So I'm going to put it somewhere here, somewhere there, and further down here. 1 2 1 2. Okay, so it's very easy to use. Okay, right, repeat, right. So now we have, and then we start to level thyristor 1. This should be T1. Wait, then thyristor 3 and thyristor 5 here. Double click thyristor 5 here. So we have thyristor 1, thyristor 3 and thyristor 5, and do the connection. Okay, straight to the supply voltage, right? And then the end you have the output. Okay, we have the resistor, isn't it? So go to power, RLC branches and resistor only. You can rotate this by using the right click button. So you just simply right click the button, right? So it will rotate, place it, or you can choose the component and you can use this rotation button, rotate button here. You can do that as well, right? So either right click or use this button. Right, now I'm going to connect that to there, there. Oh, sorry. It will be common, isn't it? So the cathode will be common. Then delete that first. Put somewhere here. Then I'm going to connect to the common. Okay, and then goes back to the neutral point. This is the neutral of the source. We also need to put in the ground. So where is the ground? Go to sources and there will be a ground here. So you can put either here, anywhere. So this is the reference point, ground, right? So that is a ground. I'm going to change that to 10 ohm, double click. So you can put it as a R load if you like. And the value is 10 ohm. Okay, 10 ohm. And what's next is the getting block for each thyristor. Great. So the getting block can be found. Go to elements again, and you go to power, switches, and look at the bottom of the switches. There's a getting block, right? So rotate again. I'm going to rotate that. So that will be the first pulse, and then the second pulse, and the third the red or sorry, thyristor 1, thyristor 3 pulse, and thyristor 5. That's 5. Let's configure the thyristor 1. So remember, thyristor 1 only trigger at 30 degrees, right? So alpha will start from 30 degree of red phase, zero crossing of the red phase. So 50, so we need to change that to 50, which is equals to the main frequency. Okay, and number of point is 2. So if you have a number of points of 2, so it will recognize the first point here as a 0.1, 0 degree. And then if you have 180 degrees, so you have a long pulse. So you start at 0 degree, and then you end up at 180 degree because only 2 points that you select. If you select 4 points, for example, and you when you do a 4 point, then actually what you want to do is you want to have 2 pulses, 3. So you do this. So 1 point, 2 point, 3 point, and 4 points, and then it repeats by 50 hertz frequency. Okay, so in this case we only need 2 points. So it's uh, remember alpha is 0 only at 30 degrees, isn't it? So you can follow the what you see here. So you just put a bracket to mark it as the delay of the getting block. So 30 plus whatever alpha is. So here we start with 10 degree, isn't it? And then we have 32 short pulse plus also 10 degree. Yes, so you have short pulse, you have 30 plus 10, 32 plus 10. So that will be the triggering angle for thyristor 1. And for thyristor 3, 2, so I'm going to, I don't want this 50 hertz. So that will be also similar to here. Now I'm going to have 50. And it start at what? Start at 150 degree. Okay, start at 150 degree. So I'm going to do this 150 plus alpha again 10 degree, 152 plus 10 degree again. This is G3. Okay, getting block for G3. Right, we'll put it somewhere here. And lastly, we have what is it? T5 only on at 270 degree. Okay, so change to 270 degree. 270 0 plus 10 degree, and we have 272 degree again plus 10 degree. So that's for G5. G5 getting block for thyristor 5. Double click. I'm going to display this. Then we have that. Okay, so we have getting block for thyristor 1, getting block for thyristor 3, and getting block for thyristor 5. Okay, next is to then we put in the voltage probe, right? The voltage probe. So the voltage probe is can be found from elements, and then you have other, and then go to probes, right? So I'm going to have voltage probe. You have two types of voltage probe. This one is only referred to neutral or to the ground. If you select this is only one terminal voltage. So if you put it here, so you will measure from that point to the ground, this point to the ground again, and that also to the ground. And if you put it here, you will measure from this point to the ground. But if you select the other one, L1, other probes, and we have only another one which is voltage probe to probe, then this will be used for if you want to measure the voltage across the thyristor 1, for example. So the dot here actually determine the dot here actually the positive terminal, right, of the probe. So if you want to measure positive negative, so make sure that the dot here at the positive terminal, right? So that is again double click. So I'm going to put that as a VT1, right? So VT1. So it will measure voltage across thyristor 1. Okay? And you can also find the probe at the bottom of the screen. So here we have a single node or single terminal and two nodes we have a, if you want to measure 2 nodes, and this is the current probe. So I'm going to select this again and put it here. And another one is V red, V yellow, and V blue. So now let's label it. So V red, V red, V yellow, and V blue here. And this is the V out, if you like, V out. And also we have this output current, isn't it? We want to have this output current as well. So we need to disconnect that, and that should be in series. The current probe should be in series. And again, there is a note dot here, so that tells us the where is the current entering the current probe. So so the current flow in this way, is it? Oh, that's it. I'm going to put again. So this will be I naught, right? I naught, and connect that to that point. Okay, then we have this I naught, right? V naught, I naught, and the output. So V out measure from that point to that point. Okay, so that is very much the how to set the circuit, 3-pulse circuit, half wave rectifier. Before we simulate, let's look at, we need to put in the simulation, and then we need to have this simulation control to define what is the time step, what is the total time, and what is the print time. This is very important before you simulate the circuit. Just forget about that. Just focus on what is time step, what is the total time, and print time. In order for you to determine what sort of total time that you need to put in, the total time actually equals to the simulation time. Okay? Total time equal to simulation time, how long you're going to simulate the circuit. So for this 50 hertz circuit, one cycle will be equals to 1 over f, is it, the t. Okay, so that will be the one period or one cycle, so which is equals to 1 over 50, so that will be equal to 0.02 second, isn't it? So in 0.02 seconds, you will complete one cycle of the waveform, the supply voltage, etc. So now for the total time, we normally let it to reach its steady state. So I still hope you still remember when you do the control signal and system, control signal system, we there is a plot of how the system react after it starts, isn't it? So here is known as transient, okay, period, right? Transient, and here we reach the steady state condition, isn't it? So uh, for us to analyze the circuit, we usually look at the steady state operation. Once it reach the steady state values, for example, if you want to measure the output voltage, once the output voltage reach the steady state, then we measure everything, isn't it? So you cannot measure the output voltage when it's still climbing this we call it the steady the signals system here, Okay, so we need to look at the characteristic of the signals. So we only focus at the output. So you need to let the simulation time to be few cycles. You're going to simulate for few cycles. Normally, just put a 5 cycles if you like. Try 5 cycles and look at the output voltage, current, whether it settles to its steady state condition. For example, if you talk about sinusoidal waveform, if you expect to see a sinusoidal waveform, so that sinusoidal waveform is observed, okay, is displayed in the simulation, and it reach one value. You don't want to see some unstable voltage display in the simulation, right? So for 5 cycles, 5 multiplied by 0.002, so it will be 0.1 second. Print time is and before the print time, let's look at the time step. So time step actually determine whether you have a smooth signals or not an accurate waveform. Because the larger wave time step, you can imagine if you try to plot the sinusoidal waveform, isn't it? Let's say this is sinusoidal waveform. Sorry for the sketch. Right, let's say this is a sinusoidal waveform. If you have a large delta t, so what it does is, the simulation does is, it will convert all this parameter, all these components into equations, differential equations, complex equation, and they solve that equation based on the time. So you start at 0 seconds, and the first time that you will select is, for this is default rate, 0.0000, and 1, 2, 3, 4, another one. Sorry, this is 1. Okay, 1, 2, 3, 4, 5. Okay, this is why we put it as 1 to the power of 10. It actually is the power of 10 minus 5. So we have 1, 2, 3, 4, 5. So the first time that will use to calculate all the parameters, the output voltage, everything, is at 0.0001, which is very, very small. Okay, so let's say somewhere here. And the next will be 0.00002, just very close. So if you connect all these points, you will get a smooth sinusoidal waveform, compared to if you have a large time step, right? Large time step, for example, 0.001. Large time step, which is 0.01. So you start from there, probably the second point will be there. First point is 0, then this, and then that. So when you connect this, because between point and point, it will be a straight line. Okay, if you connect, it's a straight line, so you won't get a nice sinusoidal waveform, isn't it? But you actually record less point. You calculate with a less number of points. But if you use some very small numbers, you have more points to be safe, isn't it? More points to be safe, and that reflects the reflects. Affect the simulation point, number of simulation recorded, because for simulation, for demo version, you can only have 6,000 point recorded. You only have 6,000 point for the demo version, and therefore when you simulate, you must have you need to make sure that you record and you see a nice steady state waveform display, right? Because when you start with 0, when it reach 6,000 point, because of demo vision, it will stop for example, at the beginning, and then it reached there, for example, it's already 6,000 points, so it will stop at that point. So you don't get a complete sinusoidal waveform, even one cycle. It doesn't reach one cycle yet. But because this is too small, and then it's already recorded 6,000 points, it stopped at that point, and therefore you won't be getting a correct answers, correct results, right? And therefore that's why we need this print time. Okay, so print time will tell Psim where to start to record the points. Okay, so if you let it 0, you record from the beginning. Let's say we're going to simulate for 5 cycles, right? 5 cycles. Okay, 5, 1, 2, 3, 4, and 5. You stop at 0.01. Okay, let's say we only want to 0.1, 5 cycles, right? So you don't want to, you just want to forget the first 3 cycles, for example. Okay? And therefore, your print time should be start at 0.06. Is that it? So you tell the Psim print time start at 0.06. So it will start to record the points from 0.06. You have 0.08 there, and 0.08 and 0.1 there. So you will observe that the output voltage will become, the waveform will record from, sorry, 0.12, is it? 3, so this is 0.06, sorry. Okay, 0.02, 0.04, 0.06. So you will record starting from that point. So you'll be seeing that waveform at the end. So, and less cycles, but then you make sure that you record properly. The number of points are recorded properly, and you get the steady state operation. So you run at 5 cycles, and you start only to print at 0.06. So you record the last 2 cycles, right? So now I'm going to change that to 0.06. Okay, right, done. Then we're going to simulate, run simulation, hit that button. Never mind, time set has been changed to 5K, don't worry. See the maximum number on data. Let's have a look. V out. Look at that. It's already reached 0.06. This is V out, isn't it? So let's have a look again. Now this is too small, isn't it? So let's e to the power of 5. Let's try again. Okay, let's have a check to the, let's check the getting block. 50 hertz. This is 50 hertz, should be no problem. T5. All right, so this is why we keep on changing the step size to smaller step size, because it's 5,000 here. So it's the wrong frequency. I'm going to check it's 50. Then let's simulate again. Leave it as a default value. Default value is 1 to the power of 10 minus 5. So I'm going to go back to the default value 0.06. Now let's try to simulate, run simulation. Then it's okay now. So let's have a look at the output voltage. That will be the output voltage. And let's have a look at the V red, V yellow, and V blue. There you go. So one cycles, two cycles. So we have one cycles, two cycles. And if you look carefully, it really smooth sine wave, isn't it? Okay, it really smooth sine wave. And this is, if you look further, so here we have 30 degree, yeah, the starting of the alpha. So if I can move up here, okay, and from there to there is actually 10 degree, isn't it? Okay, 10 degree. So once you have that, then you can display again the current if you like. If you want to have another probe, just click here. If you want to have another waveform, just click here, and then I'm going to look at the current I naught. So that will be the output current, output voltage, output current. I think I missed the input current, so I'm going to break that and put in the current, red current, or thyristor 1 current. Okay, I'm going to double click that. So this is IT1. Okay, also we have VT1. So run mention again. There you are. Okay, double click here. Then I'm going to use put in IT1. You can change the curve, how thick the thickness of the line by click this button, curves, and then you can change the color, and you can change the thickness of your current here. Then click OK. So let's have a look. So we have I naught, and this is the input current. The input current, and this is the thyristor current 1. Thyristor 1. Right. So next is to measure. How to measure the waveforms on the here. So I'm going to delete that. Just leave it there. Right? So we're going to measure the average. So to measure the average, you use this button, X with a bar. So that will give the average value of each waveform in the display in this machine. So X bar. If you want to have RMS, then you click that. And if you want to have a modulus of X, whether it's a negative, positive, you still get the positive value of average. And power factor. So if you want to have a power factor, make sure that you have voltage and current in the same plot. So you have voltage, so let's say input voltage and the input current. The thyristor 1, isn't it? So this is thyristor 1. So you need to put in one plot, and then you just hit this power factor. Okay, if I can show you, let's do the the average first. So just click this X bar. So it will give you the value of 275 V out. So the average of that. So you can compare with the theory to get this 275 with a 10 to the power 2. So 276 voltage. VB, V red, V yellows, very small numbers. Why? Because the average is 0. It's a sine wave, so of course you get the 0 numbers. So it's very small numbers, is actually 0 average value. Then I naught is simply actually output voltage divided by R. R is 10, isn't it? So you get the 2.759, 27.59. And then this is the average of IT1. So you also can calculate the average of IT1. So that is the measurement here. And if I want to look at the power factor, what I need to do is I'm going to combine okay, double click here. I'm going to remove I naught, and then I'm going to put in red phase voltage. So we have red phase voltage and I phase T1 or red phase current. T1 put in together. Then you simply click this power factor PF button. Click that. Then so it only gives that the last waveforms there, because there are voltage and current, and that's why it calculates properly. So it is 0.68 percent power factor of 0.68. And if you want to measure the output power, again put in combine the output voltage and output current, then you can calculate for the real power as well as the what we call it, the apparent power S. Okay, and this is by using the discrete. So you can actually explore, and in this case you can verify that in the nodes there is a region of continuous and discontinuous operation. Okay, so you have to compare with theory as well as the simulation to help you to understand the theory actually. So you have this theory, you sketch the waveform and get all the angles correct, and then try to increase the alpha until you reach the boundary between continuous and discontinuous. So in this case, for 3-pass half-wave rectifier, it's already identified here that the continuous output or output current and output voltage is from alpha equals to 0 up to only 30 degrees. Okay, so you can sketch and look at the waveform, how it react. Okay, so this is 30 degrees, isn't it? 30 degree. And then we have this is 90 degree, and that is 150, and this is 180 degrees, isn't it? Okay, so from there to there is 30 degree. Okay, so you can move, you can try to move alpha and look at the plot of the waveform. So if we reach from there is 10 degrees, isn't it? And then you further increase alpha, and you can see that it will go up to this point, which is alpha equals to 90 degree, and it will touches the 0 levels there. It touches that 0 levels there. Okay, so identify all of this, and if you go alpha beyond that, beyond this point, it will become discontinuous operation. So the note tells us that this is the case number 2. Alpha is discontinuous from 30 degree to 180 50 degree. So when this is alpha equals to 0 degree point, and this is when you have alpha is 0, alpha is 30, alpha is 60 degree. So here is 30 degree. Alpha, now the condition is alpha equals to 60 degree. So when you do that, so thyristor T1, T3, T5. So thyristor 5 will only operate up to that point, and because there is no current uh, to push it, to force it to stay on, so thyristor 5 will be turned off, and there will be zero output voltage until you trigger thyristor 1 again. So that's why we have this discontinuous operation, discontinuous of the current and voltage. Okay, so I want you need to understand theoretically, and you can prove that by using the simulation. So in this case, you need to change that. For example, have a look. Let's change that to uh, 30 degree. Okay, so here I'm going to change that to 30 degree, and that is 30 degree as well. And then change this to 30 degree. This is also 30 degree. And finally, that one, 30 degree. And this is also 30 degree. So let's have a look. When we change the alpha equals to 30 degree, run the simulation. Have a look at the output. So look at that. So if you look closely, now it reached zero level, isn't it? The voltage here reached zero levels, exactly as zero levels, because from here, that is zero angle of alpha, up to that point is 30 degree. From here to here is 30 degree, and the current still, and voltage also, this continuous waveform is still continuous waveform. And if you further increase the thyristor, which is the thyristor, let's say 60 degree. I'm going to change that to 60 degree now. 6 6 6 again, 60 degree, 60 degree. Okay, simulate that. Simulation, run the simulation. Okay, look at that. So it become discontinuous. It become discontinuous. So I'm going to show you the waveform as well as the plot. Okay, so you start from 30 degree, and then you end up at 30 degrees. So this is 30 degree, and therefore the current voltage will flow until that point. Okay, for 30 degree, and then there is no, when it goes beyond then 30 degree, okay, so since this is a purely resistive flow, there is no current to force thyristor 5 to stay on, isn't it? So thyristor 5 will be turned off exactly after 30 degree. And that's why you have this discontinuous up to 60°. So beyond 30°, for example, in this case, we have a 60°, and after we trigger thyristor 1 at 60°, then we'll see the output voltage waveform again, and that follow thyristor 1 or the voltage, phase voltage, until it reach that point. Then it go further and do that. So this is the output voltage that you obtain, right? So that's actually help you to understand the theory, as well as by using this information that actually assists you, helps you to understand the waveform, the operation of the thyristors. Okay, so that is by using the discrete components. Right, so now let's move to how to generate, how to simulate using the block set diagram, block set of the rectifier. Okay, so I'm going to start with a new, oh sorry, this is not the, switch to Psim. Okay, so I'm going to start with the new worksheet, and let's have a look at the component here. So this is the component for the right side here. See the component for the block set components. Okay, so you're going to choose the block set and then how to get this component. So here I already listed where you can get this step voltage, right? The step voltage, the alpha controller, where you get this comparator as well as the voltage sensor. So all actually displayed here. So you have element, sources, voltage, get step. For the sensors, okay, voltage sources, voltage sensors, element, other sensors, voltage source. So you follow this, and here you can find the component. Right, so let's have a go. So just a plain circuit. So I'm going to start with again with the element, sources, sine wave, voltage, three-phase sine, quickly. And then what's next is the block set. To get the three-phase block set there, three pulse rectifier. So you go to power, switches, and then at the bottom here, look at that. We have single phase diode bridge, three-phase diode bridge. So we want to have single phase, three-phase half bridge, isn't it? We want to have a three-phase thyristor half bridge. Six-phase, three-phase full bridge. This is a three-phase full bridge, and this is three-phase half bridge. Full bridge, half bridge. So I'm going to use that three-phase half bridge. Put it there. And next, the voltage source. Okay, how to get that voltage sensors. So let's connect that first to here. There. And then elements, power control, sensors, element, other, go to other, go to sensors. Want to have a voltage sensor. So put it there. Then comparator, element, where is the comparator? Control, and then comparator. This is the comparator. The next, the alpha controller. So it's our elements. other switch controllers alpha controller. Okay, this alpha controller, and then remember you have this ground. Don't forget about this ground, that ground. All the ground should be connected to each of the component here. So do that, right? Then you can properly configure all the waveform, the components here. For example, double click the voltage sensor, just leave it as a gain 1, right? Voltage sensor gain 1. And then you have this comparator, double click, just leave it as a comparator, no problem. And then alpha, the frequency is 50 Hertz, right? Pulse width is 120 degrees. So just leave it as 130 degrees. So make it a large pulse width. Okay, compared to the short pulse, we do the long pulse here is 120 degree. Okay, so I'm going to display the component here. So 50 Hertz with 120 degree pulse width, and it requires the triggering voltage as well. So that is supplied by the step voltage here, voltage step, voltage step. So where to get at? Element, sources, voltage, and step. Use this step. Do that. And then double click. Just simply put it as 0 seconds. 0 second and 1 V-step. Then connect all of these. Remember, this positive goes to positive of the voltage sensors here go to V red, and the negative here will go to blue waveform. Why? Because we want to detect this point. We want to tell the we want to synchronize the alpha controller to that point. So you need to sense the red phase voltage as well as the blue phase voltage. So red phase voltage minus blue phase voltage becomes 0, and that's why you compare with 0 ground, the ground which is 0. So it will trigger the alpha here. So it will tell alpha where is the location of that 30 degree. Okay, so that's why we need that voltage sensors. And then we connect to that, and this must be grounded, and connect that. Sorry, it's wrong. And that one as well, and the rest refer to this we call it the schematic diagram. Okay, refer to this, complete the circuit, and let's have a look. I'm going to is this the completed? No. Open. Okay. Okay, I already have that. Okay, once you complete all the components there, now you have this circuit. Okay, so again, similar simulation control here. Okay, simulate for here you have I put it as a 10 cycles. 10 cycles, 0.2. Then I'm going to start to record only last 2 cycles, so it becomes 0.16. I leave it as a default value, 1 to the power of 10 minus 5. And then let's simulate this. Run simulation. So you will get the same output voltage waveform. Compared to, same voltage waveform as you did for the discrete components. So here you don't have to very it's actually simplify your shortcut. Give a shorter time for you. Just change that value. If you want to change to 120 degree, for example, let's have a look. If you have a alpha equals to 120 degree, what happens to your waveforms, voltage, current as well? So here you only change one parameter, but if you use a discrete component just now, you need to change how many? 1, 2, 3, 4, 5, 6, isn't it? 6 parameters that you need to change. Here you have only changed one, which is the amplitude of the DC voltage that actually determine the angle in degree. So I'm going to have 120 degree, then go for the simulation and look at the output voltage. There is 130 degree. Okay, let's move further. Whatever is, we have 150 degree. Run simulation. So it become, look at that, sinusoidal. No, this is a very small numbers, which is actually equals to 0, isn't it? And this is very small numbers. If I change the axis, how to change the axis? Go to either X or Y here. This is X axis, this is Y axis. If I'm going to change the Y axis, just click that Y, and then instead of auto scale, let's change to oh, 240 volts, is it? 240, just put 200. The sine wave actually have the 240 multiplied by square root 2, is it? Want to have a maximum 200 square root 2, so you can write that. Oh no, cannot. Oh, this is in, sorry. Auto scale for Y axis, I'm going to have, just put 100 volt from, this is 100 volt, this is the minus 100 to 100 volt. Just click OK. Look at that. That actually 0 voltage. So if I combine with a VRAD, this is what I get. I can actually auto scale again, and then that's what I get. So I have a value of VRAD, and the output is actually 0. So compare that with the theory. So you will be confident with the theory, and that will help you to understand the whole circuits. So that's why I all emphasis, really put emphasis, or want you to know how to simulate using the Psim, because it helps you a lot in understanding the Psim, and you can use this Psim again for your for other classes when when it relates to electrical circuits. Okay, yes, you can use a MATLAB Simulink as well, but I found for Powertronic, to understand the circuit, Psim is good enough, very user friendly, and it's good enough. So because you can look at the measurement here, if you where is it here, you can actually look at for power factor, real power, as well as the THD. You can also compare that with the theory when you do the THD of current, isn't it? And we have done the square waveform, isn't it, before, and we found that the THD for the square waveform is 45%. So you can compare by using Psim, and then you can compare the results. Okay, so I hope it helps. Please, again and again, I hope this is very useful, step by step, to show how to use the Psim, and hope that it will help you in this study of power tronic circuit. Okay, thank you.